Okay, so now let's talk about poles. Okay, first we have the easiest one called removable singularity. So let me remind you, if you have a function f of z equal to its Laurent series, so you have this around z naught. So if you have this and a of, so all the negative guys are 0 for k bigger than 1. In other words, this is equal to, a0 plus a1, right? 1. So there are no negative terms. Then z naught is called a removable singularity for f. Good. All right, so let's do, yeah, let me do a different example. They have one in the book. I'll do a different one. Uh, we have the function f of z e to the 2z over z, and we claim that z naught equal to 0 is removable. And I will explain the terminology with this example. Why is it called removable? So give me a second. Okay. Uh, we simply Taylor expand, right? So we Taylor expand the top. So f of z is equal to 1 over z. And what do I have? So k starts from 0. Um, 1 over k factorial 2z to the k minus 1. The 0 term disappears. Okay, so it starts from 1. And let's bring in the z. So z to the k minus 1. Good. All right, so let me see a couple of terms. Or you can see it from here, but anyway, so we have 2, and then we have 2 to the 2 over 2 factorial, and then z, and then, and so on, 2 to the 3. Okay, so we see that, a of minus k are all 0 for k bigger than 1. There is no principal part. Let me write it this way. Where is it here? Um, there is no principal part. Okay, no singularity part. Now this is a bit surprising. You see this z on the bottom, you will think that 0 is a problem, but it's not. So long story short, if you take the limit as z goes to 0 of this function f e to the 2z minus 1 over z, well, what is it? All these guys, let me write it. We have 2, then we have 4 over 2z, and all these other guys, but they're all powers of z, so they're oz. Let me write here, oz squared. So they're all gone, and all you're left with is 2. So, so we can define a new function. We can extend f at 0. Meaning, let me write it here, f of z is equal to e to the 2z minus 1 over z when z is not 0. And when z is 0, we we define it to be 2. So that's what it means to be removable singularity. Um, because of course, at z equals 0, you cannot write this down because you get this thing, which is ill-defined. You have 0 over 0, right? So that doesn't make any sense. So you do have to take a limit and define this to be the function. Okay? So that's why it's called removable, because we removed what's happening at 0 and we put down a concrete value. Okay, so that's it for removable. Now let's talk about poles. That's the biggest part for this course. Pole of order n. Okay, so um, again, you have a function. So we have k in the integers, ak z minus z naught to the k, and you have um, you know you have that a of minus n is not 0, but a of k, a of minus k is 0 for all um, k, for all k strictly bigger than n. So these are all positive numbers. So what do I mean by that? So let me write it down. Um, i.e., the highest, most negative power is z to the minus z naught to the n. Then we have a minus 1. And then we have the analytic part and so on. Um, so this is the lowest power. All the other guys disappear. Okay. So if you have this, has pole of order n at z naught, meaning as you zoom in to z naught, this guy blows up the fastest. Okay, so I will make this more concrete with examples. Um, as with zeros, an equivalent way is the following: the function z minus z naught to the n f of z is analytic around z naught. Okay, so you pick the for for the largest um, sets n. Okay, so for 0 you pick the smallest. For the pole you pick the largest. Yeah, so let's do some examples to get a feeling. So what's going on here? Okay, let's start with a ratio. So we have f of z equal to 3z minus 1, and I have this polynomial. Let me see. Yeah, it's fine. Plus 5. Mm, okay. All right, this looks quite complicated. So first let's find all the poles, which are the zeros of the denominator. So if you factor it out, you get your z minus, I think I took this from the book. Yeah. Okay, minus 2 plus I squared. Okay, so that's your function. Now the question is, so the poles are z naught equal to minus 1 plus minus 2I. So these are the two poles, but what is the order? Okay. Um, so there's two ways. One, you could find the Lorentz series, right? Um, so let me just do that because it's not hard. It's just partial fractions. Okay, so if you do partial fractions, you have the following. Let me call this A. So Z naught, just to make our life a bit easy. So this is Z minus A. Um, wait, no, this is B. Yes. So Z minus A, and then 3 half plus I, Z minus A to the 2. Good. So let's see. For Z naught equal to B, the largest, most negative power is n equal 1, right? So there is no other uh, negative power for z minus b. And if you like, a way to check it more formally is you multiply by z minus b to the n, and you have z minus b to the n minus 1, um, z minus b to the n with this entire function, call it g. Okay, um, and then you take a limit. So as z goes to b, um, this guy goes to 0, and this guy goes to 0, only when n, is bigger or equal than 1. Okay, um, right, and right, but that's right. So it is analytic for these guys, but we want it to be non-zero. Um, so let me do this more carefully. Okay, so first of all, it's analytic for n greater or equal than 1, and it's not 0 when n is exactly 1. So let me write like this. When n is less or equal than 1, so if you take these two together, n is forced to be 1. Okay? But anyhow, so whatever you find more comfortable, either you take limits or you just find the Laurent series and just look for the exponent. So up to you. Um, okay, good. All right, so let's do another example. Um, cosine z cosine 2z over z6. All right, so first you have to find the pole, and you just have to look at the denominator because the top is analytic. So the only pole is z not equal 0. Now you might say, well, isn't it obvious that it's 6? You know, it looks, well, no, because the top guy, you have, let's put 0 quickly. We have cosine 0 minus cosine of 2 times 0, but these are both equal to 1. So the top guy will contribute to the power. So we have to be careful and expand. So let's find, um, yeah, let's find the Taylor series. Sorry, let's find the Lorentz series and then pick up the coefficient, the most negative. All right. So f of z is equal to 1z6. And then let's see, we have minus 1 to the k, 2k factorial, z to the k, and right, minus, yeah, it's the same coefficient, but it's 2 times. So 2 times z to the k. All right. So I subtracted the two Taylor series. Okay, good. Now let me take out the 2 and let me bring in the z to the 6. Okay, so this is 1 minus 2 to the k, and then c to the k minus, sorry, 2k, yes, minus 6. All right. Good. So let's look at the first few terms. So if I put k equals 0, I get 3 halves over z to the 4. Um, the next one is minus 5 over 8 z to the 2, and constant term 780. So yeah, and then it's just constant terms. So this is the analytic part. All right. So then you just stare at the series and you see that this guy has the most negative power. All right. And so f of z, let me write the series, the function, just to point out something, has order n equal to 4 at z equals 0. So the top guy contributed a z squared. Okay, so it's not 6. It is not n equals 6. All right, so you have to expand the top to see what's happening. Okay, um, let me finish up with essential singularity. So essential singularity definition, at z naught, when the order of the pole is infinite. So is n equal infinity. Okay, i.e. a minus n is not 0 for all n bigger than 1. Okay, so let me do the most simple example. just take your exponential z minus 1 and expand around 1. So just use the the usual expansion for the exponential because it's defined everywhere. Okay, so we have this, and we see that you can start from constant term 1, and then there is no um, squared. There is no smallest negative power. You can keep going, and you have more and more negative powers. Um, okay, so let's do another example. F of z equal to z to the 3 sine 1 over z. Again, we expand the exponential, sorry, the sine term, minus 1 to the k, 2k plus 1, and then 1 over z, 2k plus 1. Okay, factorial here. Um, so yeah, let's bring in the cubic term. So I can just write down the series. So minus 1 over 6, 120 z squared, and o z squared. Okay, so again, um, there is no largest negative power. Okay, so z equals 0 is an essential singularity for f. Okay, good. So that's it for